All right, you guys, welcome to today's segment of Ms. Olson Tries to Record Notes. Today we're going to be talking about drawing Lewis dot structures, and Lewis dot structures are a shortcut for Bohr models, and they end up being really powerful for us to look at covalent compounds and think about the shapes that the molecules have in 3 dimensions. So what are atomic Lewis structures? A Lewis dot structure or Lewis dot diagram is a diagram representing the valence electrons in an atom. So it's really just a simplification of the Bohr-Rutherford model. Instead of showing every energy level and every electron, it only shows the valence electrons. And what we've started to talk about and emphasize is this idea that the exterior electrons, those outermost valence electrons, are the ones that actually do the chemistry. The rest of them on the inside kind of just hang out. They don't get traded away or anything dramatic like that. So when we draw a Lewis structure, we take just that outermost ring and we represent its electrons. So in the case of potassium, there's only one valence electron. So there's only one dot on the Lewis diagram. So this is the most commonly used thing to depict our covalent bonds and molecules. And it consists of just the atomic symbol and the valence electrons around it. It's very simple, very straightforward. So how do we draw a Lewis structure for a single atom? We got to start with the basics before we can move on to drawing Lewis structures for something more complicated like a molecule. Okay, so here are the steps to follow. First of all, you need to determine the number of valence electrons. And you can do that by looking at your best friend, the periodic table, and seeing which family it's in. So then you can either draw a Bohr model if you wanted, or you can just use the rule. Group 1 has 1 valence electron, group 2 has 2 valence electrons. Skip the transition metals. Group 3 has 3 valence electrons, group 4 has 4, and so on and so forth across the table. Then you'll write the chemical symbol, the atomic symbol, to represent the nucleus. Then you're going to draw a dot for each valence electron. Some other rules just to keep in the back of your mind when we're dealing with Lewis structures are the following. There's a maximum of 8 dots or electrons in a Lewis structure. And this is because the true valence of a compound is going to incorporate that P6 level. And so it'll end in like S2P6. So there's really only 8 dots or electrons that we care about in covalent bonding, right? Metals can do whatever they want, but in covalent bonding, we really only care about nonmetals. So there's a maximum of 8 dots. And then single dots are called unpaired electrons. So if you have a single dot by itself, it's an unpaired electron, just like that half arrow that we would see in our electron configurations when we would draw out the orbitals. So if we look at this slide, this is a concise look at the Bohr models for the first handful of elements. And you'll notice it stops before the transition metals begin. In this particular case, where we're really going to be focused on covalent bonding, all we care about pretty much are the nonmetals. So we're going to be looking at carbon, nitrogen, oxygen, fluorine, chlorine, sulfur, phosphorus, silicon, right? We're just going to be focused on those nonmetals. Like we've discussed before, the noble gases, even though they're nonmetals, they don't tend to bond because they already have that full valence with 8 electrons. So they're like, whatever. They're not really worried about gaining or losing electrons. So let's look at a couple examples. We will look at 2 nonmetals and 2 metals just for the sake of comparison. So we have nitrogen and phosphorus. They each have 5 valence electrons. And you can see that their Bohr models look different because phosphorus has an extra energy level in it because it's a bigger atom. And then we have magnesium and calcium, same thing. They both have 2 valence electrons, but calcium has an extra row of energy levels because it has more protons and so it has more electrons. So then if we draw the Lewis structures, what we notice is that they look exactly the same if they have the same valence. So even though we know that phosphorus is bigger than nitrogen, when you draw the Lewis dot structure, nitrogen and phosphorus look the same. And indeed, nitrogen and phosphorus tend to bond very similarly. They're going to act really similarly because they have that similar valence structure. Again, magnesium and calcium are the same. They have 2 valence electrons, and when you draw their Lewis structure, you can't necessarily tell that they want to, or that they have 2 different sizes, that their Bohr models are so different, but they are. Sorry I keep coughing so much, you guys. The smoke is getting to me a little bit today. Okay, I want you guys just to take a minute, think about how many valence electrons each of the elements listed here have, and just draw a quick Lewis structure for them. So go ahead and pause the video and do that, just so that you know that you can. You can identify valence electrons accurately, and you can draw the Lewis dot structure. So here we go. For aluminum, you should have found 3 valence electrons, and so aluminum would have 3 dots. Fluorine has 7 valence electrons, so it should have 7 dots. Sulfur has 6 valence electrons, so it would have 6 dots. Sodium just has 1 valence electron, so it would just have 1 dot. Very straightforward. Okay, so here's where it gets interesting. How do we use Lewis structures to depict bonding? How can we draw 2-dimensional pictures of molecules in covalent bonding? So to get into this, we want to think about why do nonmetals form covalent bonds in the first place? And the reason they do this is something that we call the Octet Rule, which is that atoms need a full valence shell with 8 electrons, so that would be S2p6 in the same energy level, to be stable. They want those 8 electrons. That makes them very energetically stable. So there's a couple different ways they can do that, right? They can trade electrons, or they can share electrons. And we're really interested in covalent bonding. We're interested in sharing electrons to get to 8 electrons. Hydrogen and helium are a notable exception. They only need 2 electrons because they're so tiny, right? They just have that s orbital to deal with. So atoms share electrons in covalent bonds to have a full octet. If you're like worried that you're going to have a hard time remembering how many electrons they want to have, think about it is the Octet Rule. Oct is a prefix that refers to 8, like octopus or octave or octagon, right? It refers to 8. Also, I just really like octopi. They're cool, but I'm also kind of terrified of them. But I sort of want to pet one, but that just seems unfair to the octopus. Anyway, so let's delve into this a little bit deeper by looking at some models. So I like these models because they show the Bohr drawing type of model, like an energy level model, and they show the Lewis dot model. So it's kind of the best of both worlds as we're making that transition in our thinking. So in the energy level model and the Lewis dot model, which I've boxed in red for you, what do the pair of dots between the 2 letters H, right, so the 2 hydrogens, what do those represent? So hopefully you can look at this and say, all right, those are the electrons. So the dots, whether that there's an energy level model or it's just the atomic symbol of the Lewis dot model, those dots are representing our electrons. So then, to simplify that, because chemists are lazy, we make a line instead of the two dots. So a single line in a Lewis dot diagram represents 2 electrons. Okay, so a line is equal to 2 electrons. We often call these 2 electrons a bonding pair. Okay, because they're used to hold the molecule together. Okay. So then, once our hydrogens are close together, do they have a full set of electrons? So this is a question we want to ask. And the first energy level is tiny, right? So it can only hold up to 2 electrons, which means that for hydrogen, when it's sharing 2 electrons, then it does have a full set of electrons because each hydrogen thinks it has 2 because they're sharing. And if you are an atom, sharing is caring. So let's look at a little bit more complicated example, but this is also one that's kind of familiar to us. So we have water, H2O, and we want to think about how does a water molecule fill the outer energy level of the hydrogen atoms. So there's 2 hydrogens, 1, 2, and then how does a water molecule fill the outer energy level of the oxygen atom? So if we look at this, we can see that oxygen has 6 electrons and it wants to have 8. Hydrogen has 1 electron each and it wants to have 2. So what we end up doing is the hydrogen shares one of its electrons with oxygen and oxygen shares one of its electrons with the hydrogen. Now hydrogen thinks it has 2 and oxygen thinks that it has gained an electron. So we bring in the other hydrogen, we get another sharing situation. So now oxygen thinks it has 8 electrons, and each hydrogen thinks that it has 2 electrons, so that everybody's happy. And because drawing all these dots all the time is annoying and chemists are lazy, we are using that line to represent the bonding pair. So we're saying 2 electrons are being shared between hydrogen and oxygen, holding them together, and then 2 electrons are being shared between this hydrogen and oxygen, holding them together. So if we wanted to count the electrons for that oxygen, we would count 2, 4, 6, 8. So oxygen is satisfied in terms of the octet rule. And hydrogen is also satisfied because it only needs 2. So we would count 2 from that bonding pair. Last, we have carbon dioxide. We want to think about how does carbon dioxide fill the outer energy level of the carbon atom, and how does it fill the outer energy level of the oxygens? In this case, carbon needs 4 more electrons, right? Because carbon only has 4 valence electrons. And each oxygen needs 2 more valence electrons. So here, we kind of have to double share. So this oxygen on the right is sharing 2 of its electrons with carbon, and carbon is sharing 2 of its electrons with oxygen. So now oxygen thinks it has 2, 4, 6, 8 electrons. And the other carbon is doing the same thing, or sorry, the other oxygen is doing the same thing, so it thinks it has 2, 4, 6, 8 electrons. Carbon in the middle here is sharing with each oxygen, so it thinks it has 2, 4, 6, 8 electrons, and everybody's happy. Now we can go on and simplify the notation by putting in 2 lines to represent 2 bonding pairs and 2 lines to represent 2 bonding pairs. You'll notice that in these models, they're using the dots over here to represent what we would call lone pairs, right? So they're not bonded, they're non-bonding lone pairs.